Okay, we're ready to start the second session of this morning, and the first speaker is Greg Moore, and he'll tell us about the developments in BPS wall crossing.
Okay, so I was surprised, but of course delighted to be invited to speak here. So my thanks to the organizers and for doing a terrific job. It's been a great conference. I'll be talking about some work. I've been doing with Davide Gaiotto and Andy Knightsky, and I'll be talking about a paper we posted recently. This is Davide taking care of one of our paradoxes. Here's the outline of the talk. I'll begin with a review of BPS wall crossing, and then I'll describe the Kontsevich-Soibelman formula that Boris mentioned in his talk. And then the goal of this talk is to understand that formula from a physical perspective. And so I'll remind you about a few things about n=2 field theories and what happens when we compactify on a circle. That leads to a certain hyperkähler metric, which is best understood in twistor space. And then our goal is to construct the holomorphic functions on twistor space as a series of approximations, first in a one-particle approximation, and then the full answer by formulating a certain Riemann-Hilbert problem, which will be equivalent to an interesting set of differential equations. Then I'll summarize and conclude. So this talk, as I just said, is about BPS wall crossing in 4 dimensions. And in the past few years, there's been some progress in understanding how the BPS spectrum depends on the vacuum. These are called wall crossing formulae. Now, didn't this guy already talk about that at Madrid last year? Yes, I did. I talked about wall crossing formulae derived with Frederick Denef, and I thought I was completely done with the subject, but then a bolt out of the blue in the form of a preprint from Kontsevich and Soibelman came along, in which they proposed a remarkable wall crossing formula for generalized Donaldson-Thomas invariants of Calabi-Yau threefolds. And it was clear that a physical interpretation of their result would be very interesting and useful, and that's the point of this talk. So let's begin by reviewing a little bit about BPS wall crossing. So we're starting on R4 with an n=2 theory. The moduli space of vacua will be denoted by MV, and I'll refer to that as the U-plane. Now, the Hilbert space of one-particle states in the theory depends on the vacuum U as a representation of n=2. And moreover, the low-energy theory has an unbroken rank R abelian gauge symmetry. Therefore, there's a symplectic lattice, capital gamma, of electric and magnetic charges. Generic charge is denoted by little gamma. The Hilbert space can then be graded into its different charge sectors. And now the n=2 central charge operator on a given charge sector is a complex scalar known as the central charge function Z gamma of U. The BPS subspace is the subspace of states which saturate the BPS bound. Energy is absolute value of Z. As Boris mentioned, it's useful to define an index of BPS states, which will be denoted omega, second helicity supertrace. Now comes an important physical point. Some BPS states are bound states of other BPS states. So supposing that psi is a BPS state of charge gamma, and it's a bound state of 2 BPS states of charges gamma 1 and gamma 2, then psi will decay as U crosses a wall of marginal stability for gamma 1 and gamma 2. That's a real codimension 1 wall in moduli space where the central charges Z gamma 1 and Z gamma 2 are parallel complex numbers. That's been known for a long time, was important to Seiberg-Witten theory. What we'd now like to do is be more quantitative about how many states decay. So across this marginal stability wall, let's take a 1-parameter family of vacua from U plus to U minus, and Frederick Denef and I gave formulae for the change of the BPS index for decays of the form gamma 1 plus n gamma 2, where gamma 1 and gamma 2 are primitive vectors. And this used Deneff's multi-centered solutions of supergravity and also quiver quantum mechanics. But the methods do not easily generalize when the two decay products are, neither one has a primitive central charge, primitive electric charge, excuse me, that was very confusing. Where neither of the composites has primitive electric charge, then these methods up here do not apply very well, but Kontsevich and Soibelman's formula does apply. So now the next several pages will be devoted to trying to explain to you what the Kontsevich-Soibelman formula is. So there are two ingredients. The first ingredient is the notion of BPS rays. So let's work at a generic vacuum U, and then for each electromagnetic charge, little gamma, we'll define a ray, L sub gamma, in the complex plane, call it the zeta plane, which are the negative reals multiplied by this complex number, z gamma of u. And this picture is about as close as we get to the LHC in this talk. So, now as u changes, these rays rotate around. And as u crosses a marginal stability wall, some rays will coalesce. So supposing you're near a marginal stability wall for gamma 1 and gamma 2. Well, then their arguments are nearly the same. And as we cross the wall, you see these rays coalesce. And now imagine you're crossing the wall and the rays are rotating. So when you get to the other side of the wall, the rays look like this. And notice, please, that the clockwise order of gamma 1, gamma 2 has changed to gamma 2, gamma 1 as we cross the wall. That would be important. Now, the other element in the KS formula is a certain set of symplectic transformations. So we introduce a complex torus T. It's the dual lattice to gamma, tensor C star. So it's simply a 2R-dimensional complex torus. And then this has a symplectic structure, and there are some symplectic transformations, K sub gamma, which you don't need to know the exact formula to appreciate the KS formula. In 2 pages, I'll give you the formula, but you don't need it right now. Now, what KS do is they assign a group element, S gamma, to each of these BPS rays. So it's the product over all the parallel charges, gamma prime, of K gamma prime, raised to an integer. That integer is the BPS index. So now let's look at the KS wall crossing formula. For a generic point U in a convex cone V in the zeta plane, say the cone between these heavy green arrows here, we associate a group element, A of V, which is the product of these symplectomorphisms over all the BPS rays in that cone. Put differently, it's the product over all the charges little gamma such that negative their central charge lies in this cone, and the product is over K sub gamma to the omega of gamma u. Now there are 2 sources of u dependence in this formula. One is manifest because the BPS indices depend on u. On the other hand, you see the K sub gammas don't all commute. So I have to tell you how to order this product. And the rule is that as we read from left to right, the product should be ordered by taking the clockwise ordering of the BPS rays. So there's the other source of U dependence, because I showed you that as U crosses a wall of marginal stability, the order of those rays can change, and the K's don't commute. So you might expect that this group element would change as U crosses a wall of marginal stability. The main statement of KS is that the product is nevertheless independent of U. Now how can that be? The K's don't commute and their order changes as U crosses a wall of marginal stability. The answer is that the BPS indices make a compensating change to keep the total product independent. That is therefore a wall crossing formula. Okay? Now to complete the story of the KS formula, I have to tell you what these transformations are. So here's our complex torus. And notice that there's a natural basis of holomorphic functions on this torus for each charge little gamma. there's a holomorphic function from t to c star. It simply contracts with elements of gamma star. So if we choose a basis, little gamma I, for the lattice gamma, then we get a symplectic form and on the lattice, and then we can use that to make a symplectic form on the torus. So now the Ks transformation, K sub gamma, is defined in terms of its action on the holomorphic Fourier modes. It takes x gamma prime to x gamma prime times a certain power series in x gamma. For example, for r equals 1, the lattice is two-dimensional, so t is just c star times c star. If x and y generate the holomorphic Fourier modes, here's the symplectic form. The lattice is two-dimensional, so lattice vectors are a pair of integers a and b, and KAB is this explicit symplectic form. It will reappear. Okay, so now I've told you what the Ks formula is, and it looks very abstract, and now we'd like to understand where it comes from physically. And I'm going to do that in the context of n equals 2 field theories. So let's remind ourselves a little bit about Seiberg-Witten theory. So we'll have a semi-simple ultraviolet gauge group of rank R, and the moduli space of vacua will be just CR, that's the U-plane. And now we should think of this lattice of electric and magnetic charges as a bundle of lattices over the U-plane, and as you all know, there can be monodromy on that bundle of charges. So mathematically, we say that we have a local system. There's a flat connection. To be sure, locally we can choose a duality frame, splitting gamma into electric and magnetic charges. That gives us special coordinates, AI, and then the central charge function is written out simply in this way. Now, we also need some elements of special Kähler geometry. So the lattice, the bundle of lattices gamma, or its dual, gives us a bundle of tori, because we can take the tensor product of gamma star with a circle, R mod 2 pi z. And the total space of this vibration I'll denote by J, and so this is the picture you should have in mind. Over each point in the U-plane, there's this torus. For special Kähler geometry, we need more structure. These toris have to be abelian varieties. So if we choose a duality frame, then we get a period matrix on those abelian varieties, and then we can write this famous formula for the low energy effective theory. The Fi's are the different U1 gauge fields. Okay, so that's special Kähler geometry, and what Seiberg and Witten did is they explicitly exhibited a family of Riemann surfaces over the U-plane, so we could take their Jacobian, and that gave us the special Kähler geometry. So, for example, SU2 with no flavors is this simple Riemann surface, and the vibration degenerates over the monopole and the dion point. And Bilal and Ferrari worked out very carefully the spectrum of BPS states. And they found that there was a strong coupling region near U equals 0, where there were just two BPS states, the monopole and the dion. And then there was a region infinity, where there was an infinite set of BPS states of magnetic charge 1 and all even electric charges, and the W boson. So if you write out the Ks formula for that case, they also showed that there's only one relevant wall of marginal stability. So if we look at the Ks formula across that wall, then in the strong coupling region, we have the product for the monopole and the dion. In the weak coupling region, we have an infinite product. Notice that K01 and K2-1 have changed their order, as I explained. And then we have to account for all the other dions. The W boson sits in the middle. Now these are the KABs I was talking about before. Okay? So this is some very complicated identity involving symplectic transformations, an infinite product of symplectic transformations. And look, it's either true or it's false. And it's true. Okay? So as you can prove, purely mathematically, with a considerable amount of ingenuity. So these are the kinds of things we want to explain. So how are we going to explain that? Well, the secret is to consider the theory on a circle compactification. At low energies, the theory is then described by a three-dimensional sigma model with a target space, which is the total space of this vibration. And where are the other scalar fields coming from? The scalar fields for the tori? Well, they come from the Wilson lines associated to the abelian gauge fields AI. So there are electric Wilson lines and magnetic Wilson lines. And moreover, supersymmetry tells us that the whole space has to be hyperkähler. So the rest of this talk is focused on trying to understand that hyperkähler metric. Now, in one limit, that hyperkähler metric is completely clear. You can take the radius to infinity, the radius of the circle, that is, and then it's straightforward. You Kaluza-Klein reduce that abelian Lagrangian I showed before, you dualize the three-dimensional gauge fields, and presto, you get what we call the semi-flat metric. So dz here is a one-form, holomorphic one-form on that torus. It's a linear combination of the magnetic and electric Wilson lines. Now I can explain the main idea, so wake up. Okay, so we've got the semi-flat metric, which is the leading approximation as r goes to infinity. But that's not the right answer at finite r. It's corrected by instantons. You can think of those instantons as world lines of BPS particles on S1. Therefore, the quantum corrections depend on the BPS spectrum. But the spectrum jumps. But wait a second, the true metric, if there's no particle becoming massless, the true metric must be smooth across the walls of marginal stability, and therefore that relates the quantum corrections, i.e. the BPS states on one side of the wall to the other side of the wall, and that implies a wall crossing formula. And we claim that is the Kontsevich-Sleivelman wall crossing formula. So to get our hands on this, what we have to do is understand this hyperkähler metric. And the best way to do that is to go to twistor space, which I remind you, topologically is a product of the moduli space with CP1, but it's endowed with a holomorphic structure and a map, holomorphic map P, CP1, so that the image, the fiber over zeta, the fiber over a point zeta in CP1 is the moduli space in complex structure zeta. Now, a hyperkähler metric G is equivalent to a fiber-wise holomorphic symplectic form suitably twisted on the twistor sphere CP1. And in plain English, what that means is that these fiber-wise symplectic forms depend on zeta very simply with a pole at 0 in the origin, and the coefficients here give you three closed two forms which define the hyperkähler metric. So knowing the hyperkähler metric is equivalent to knowing omega tilde. Now we've got more structure here because our moduli space is fibered by tori. And this is conceptually a difficult slide, so hang in there. So we have a torus vibration, and therefore we have a canonical basis of holomorphic functions labeled by the electromagnetic charges. Roughly speaking, they are those functions, those holomorphic functions on J zeta, which when restricted to a fiber over a given point u, look like the canonical Fourier modes associated to gamma. You see, Ju, I remind you, is gamma star times the circle, so a charge little gamma gives a canonical circle value, u1 value function. That should remind you of something. That's how I define the holomorphic Fourier modes on T, except they were C star valued. And indeed, knowing these functions is equivalent to knowing a map, depending on zeta, from J zeta to T, which is holomorphic. And then these holomorphic Fourier modes are the Poldacks of the canonical ones there. Why am I bothering you with all this? Because, you see, T has a canonical symplectic form, holomorphic symplectic form. So we're going to define our hyperkähler metric by taking the pullback under this map of this canonical form. And so now what I've done, if you got lost here, what I've done is I've reduced the problem of finding the hyperkähler metric to the problem of finding these holomorphic Fourier modes. So how are we going to do that? Well, again, let's start with the semi-flat limit. So as r goes to infinity, we have a very explicit metric, and it's not difficult to extract the holomorphic Fourier modes in that limit, and here they are. So here's the theta gamma, and then to make this thing holomorphic in complex structure zeta, you have to add the central charge function up here. So our strategy is to compute the quantum corrections to this and express it multiplicatively as an instanton correction, 1 plus exponentially small. Then we're going to recover the holomorphic symplectic form by pulling back the canonical one. Okay, so how do we go about calculating these quantum corrections? Well, let's calculate the leading quantum correction in the following situation. Well, we're near a point, like the monopole point in the U-plane, where just one hypermultiplet is becoming massless. And the virtue of that is that near that point, one BPS state is becoming light, and all the others are parametrically heavier. So the instanton corrections go like e to the minus r times mass. So the other instanton corrections are parametrically smaller. So that's what I just said. The dominant quantum corrections come from instantons of just these BPS particles. So now we can choose a duality frame where H is electric and has a positive charge Q, and therefore we can do an effective field theory calculation of the quantum corrections. Okay? Now the next 3 slides are more for experts. The result of that calculation, which is essentially a one-loop calculation, gives a periodic tau nut space. You get a given Hawking metric, which is a metric on a U1 fibration over R2 times S1. The R2 is parameterized by A, the S1 is the electric Wilson line, the U1 fiber coordinate is the magnetic Wilson line, and V is a positive harmonic function which one computes in a one-loop calculation. And the result can be expressed as a semi-flat piece plus an instanton piece. If you substitute V semi-flat in here, you're just rewriting the semi-flat metric. The instanton piece is a sum over k Bessel functions. So this is a sum over the winding numbers of the BPS particle, and the k dot Bessel function is exponentially small. Now, with the explicit metric in hand, you can look for the twistor coordinates. You first calculate omega, that's completely straightforward, and now you search for a map chi, which pulls back the canonical symplectic form to the omega. And expressed in terms of the generators of the holomorphic Fourier modes, chi electric and chi magnetic, you're trying to solve this equation, but this is a differential equation. Well, you've got a differential equation, you can go solve it, and here's the solution. The electric Fourier modes are uncorrected from the semi-flat limit, but the magnetic Fourier modes are corrected. Here's the semi-flat answer, and after 2 months of making every conceivable mistake, we finally came up with this answer here. And the road sign is here because I've taken a few literal liberties with the exact formula. What you have here is an integral in the zeta plane over the electric BPS rays. So now we see those BPS rays coming back. And I've taken some liberties to make plain the key features of the formula. And what are the key features? Well, the first is that as a function of zeta, this has a discontinuity across the BPS ray because of this pole down here. Moreover, you can calculate that discontinuity, and you see it's the exponential of q log of 1 minus x to the q, which might remind you of that ks transformation. Furthermore, the electric coordinate is exponentially small in the BPS ray, so this is indeed 1 plus exponentially small. So this slide just repeats what I said. As a function of zeta, chi-m is discontinuous across the electric BPS ray. The discontinuity is given by a ks transformation. So if you take these coordinates, these twistor coordinates, and you look at their analytic continuation in the counterclockwise direction in the zeta plane up to a BPS ray, and compare it with the analytic continuation in the clockwise direction in the zeta plane, then they are discontinuous by the symplectic transformation. It's a result of calculation. Moreover, the chi sub m's are indeed exponentially close to the semi-flat ones, as befits instanton corrections. Okay, So now comes another important point. So now we've calculated the leading quantum corrections. We'd like the whole thing. We'd like to take into account the instant-time corrections for all the BPS particles. But we hit an obstacle. We cannot use an effective field theory calculation because mutually non-local fields are illegal. Our proposal is to circumvent this problem by reformulating the instant-time corrections as a Riemann-Hilbert problem in the zeta plane. Okay, so what is that Riemann-Hilbert problem? Well, here we go. So we have we're looking for a map from J zeta to T, and it's got to be piecewise holomorphic, but we expect discontinuities across rays in the zeta plane. Across each ray in the zeta plane, we declare that its discontinuity is given by the Kontsevich-Sleivelman symplectic transformation. That defines a Riemann-Hilbert problem. We must supplement it with a certain boundary condition that says that chi goes to chi semi-flat exponentially fast as zeta goes to 0 or infinity, as befits an instant-time correction. That's the Riemann-Hilbert problem. You solve it by using an integral equation. So this is a solution of this integral equation is a solution to the Riemann-Hilbert problem. So what you see up here is a sum over all the BPS states weighted by the indices, an integral over the BPS ray, and then you see there's a discontinuity from the pole here, and it's designed so that the discontinuity across that ray is the KS transformation. Now, chi semi-flat is exponentially small on this BPS ray, so you could stick this into here and then iterate the whole procedure and get an explicit instanton expansion as a sum over trees. So we've succeeded in constructing our holomorphic Fourier modes, and therefore we've succeeded in constructing our hyperkähler metric. Okay? So now I can explain to you the conceptual meaning of the wall crossing formula. It's just continuity of the metric as we postulated before. So I remind you that as U crosses a marginal stability wall, the BPS rays pile up and change order. And what the KS wall crossing formula says is that the discontinuity, the total discontinuity, is unchanged. And if you think that through, what it means is that omega tilde, and hence G, is continuous across a wall in the U plane. Okay? So at this point, we understand the conceptual meaning of the KS formula. Now, we're not quite done yet, because we constructed a hyperkähler metric. How do we know it's the right one? How do we know it's physically the right one? I mean, we just made some proposal for how to include the effects of mutually non-local particles. How do we know it's the right procedure physically? Well, this is how. The Riemann-Hilbert problem is equivalent to a certain system of differential equations. Mathematically, you can derive this system of differential equations from the Riemann-Hilbert problem. What you do is you look at d chi inverse, and although chi is discontinuous across BPS rays, d chi inverse is continuous. Okay, so it's holomorphic. And then you use the asymptotics as zeta goes to 0 and infinity to write out the explicit zeta dependence here. So these capital A's don't depend on zeta. So mathematically, this system of differential equations is equivalent to our Riemann-Hilbert problem. Now, the main point, physically, you can derive these differential equations. So this, you see, is anomalous U1R symmetry. If you think through, the U1R rotates the zeta. This is anomalous scale symmetry. This is holomorphy of the chi's. So therefore, this system, which is equivalent to the Riemann-Hilbert problem, can be derived from physics. Okay? Now, mathematically, what this equation says is that we have a differential equation in the zeta plane with a second order pole at zeta equals 0 and at zeta equals infinity. Therefore, it exhibits Stokes phenomena. Okay? And what these other equations say is that the Stokes factors are independent of U and R, and therefore can be computed in a large R limit, but that's where the one instanton approximation is good. But that's where you can use an effective field theory calculation, and I showed you that we derived the Ks factors in an effective field theory calculation. End of proof. So let me summarize. We constructed the hyperkähler metric for circle compactifications of Seibert-Witten theories. The quantum corrections to the dimensionally reduced semiflat metric encode the BPS spectrum. The continuity of that metric across walls of marginal stability is equivalent to the Ks wall crossing formula. And we found that it was extremely good to use twistor transforms to encode the quantum corrections of mutually non-local particles. So there are other things we've done, which I don't have time to talk about, but very briefly. These chi-sub gammas are interesting objects physically. They're also Wilson and Tuchman-Melnichena loop operators and related to a certain three-dimensional TFT. I haven't stressed it, but there are strong analogies here to the TT star geometry of Jacotti and Vafa. In some sense, this is a four-dimensional generalization of that. And some years ago, Cherkis and Kapustin pointed out that the very moduli spaces I've been talking about, the hyperkähler metrics I've been talking about for a large class of n equals 2 field theories, are equivalent to the moduli spaces of certain Hitchin systems, and we've investigated that somewhat extensively. There are some open problems. There's actually quite a lot to do here. So one thing is that since we have a prescription for including the quantum effects of mutually non-local particles, it might be interesting to look at singularities at superconformal points. Then, I haven't stressed it, but there are interesting relations to integrable systems. I don't know much about what they are, but they're clearly there. And the Ks formula that I showed to you is just the plain vanilla version. There's a souped-up version called the motivic wall-crossing formula that will be related to the relation to integrable systems, and it might be interesting to study. Then there are relations to the mathematical work of Dominic Joyce, and even more strongly to a beautiful paper of Bridgeland and Toledano-Laredo. And some of their constructions are very close to ours. They use Stokes factors and so on, although the exact relation is not quite clear. For me, one of the most important things is the generalization to supergravity. Now, we've gone a certain distance down that road. A lot of the formal structure generalizes right away, and so you can just follow your nose, but then you're led to some paradoxes which we haven't resolved yet. And it would be good to resolve it, because one thing that I hope might drop out of all of this is a prescription for quantum corrections to hypermultiplet moduli spaces. And that's something we've wanted to know how to compute. That was mentioned by Boris in his talk as being an interesting thing to compute and perhaps useful for string phenomenology. Thanks for your attention.
Thank you. So are there questions?